There's something hauntingly beautiful about the universe, not just the glittering stars or swirling galaxies, but the hidden architecture holding it all together. Stretching across unimaginable distances like ghostly threads, cosmic web filaments weave through the darkness, connecting everything in a vast, invisible network. These filaments are the scaffolding of the cosmos, the hidden highways along which galaxies travel, yet they're filled with mysteries we're only beginning to unravel. What strange forces shape these colossal structures? What secrets do they hide within their faint, shimmering glow? Picture this. If the universe were a tapestry, these filaments would be the dark threads stitching it together, silent, almost imperceptible, but utterly essential. They're made of dark matter and hot gas, threading through the voids between galaxies, and yet, despite their enormity, they're some of the least understood phenomena in existence. Scientists have mapped their eerie glow, traced their faint outlines, and still they defy easy explanation. Some filaments stretch for hundreds of millions of light years, longer than anything else in the known universe, and within them bizarre anomalies lurk. Strange energies, unexplained movements, even whispers of something beyond our current physics. That's where the real intrigue begins. Today, we're diving deep into 25 of the most baffling, awe-inspiring phenomena hidden within these cosmic filaments. From mysterious radio emissions with no clear source to bizarre particles behaving in ways they shouldn't, each one challenges what we thought we knew about the universe. Some of these enigmas might hold the keys to understanding dark matter, while others could rewrite the laws of physics entirely. So, if you've ever looked up at the night sky and wondered what's really out there beyond the stars, beyond the galaxies, you're about to embark on a journey into the unseen. The cosmic web is calling, and its secrets are waiting. Let's begin. One of the most perplexing mysteries lurking within the cosmic filaments is the case of the missing baryons. These ordinary particles, the building blocks of stars, planets, and even our own bodies, should make up about 5% of the universe's total mass. Yet, when astronomers tally up all the visible matter, nearly half of it simply vanishes. The numbers don't add up, and the cosmic filaments, those vast rivers of gas and dark matter, seem to be hiding the answer. So where did all this missing matter go? Scientists suspect it's trapped in an elusive form, a diffuse, superheated gas known as the warm-hot intergalactic medium, or WIM. Imagine steam so thin and spread out that it's nearly invisible, threading through the spaces between galaxies. Detecting it is like trying to spot a whisper in a hurricane. The gas is so hot it emits X-rays, but so sparse that even our most advanced telescopes struggle to pick up its faint signal. Some of it might also exist in a bizarre, low-density plasma state, slipping through our observations like smoke through a sieve. Recent breakthroughs, however, are starting to shed light. By studying the way distant quasars' light dims as it passes through filaments, researchers have spotted traces of ionized oxygen, hints that WIM might be lurking there. Other observations using X-ray telescopes have detected faint glows that could be the fingerprints of this missing matter. Yet, even with these clues, the puzzle isn't solved. The sheer scale of cosmic filaments means that mapping the WIM completely is like trying to trace every droplet in an ocean. What makes this mystery so crucial is that baryonic matter, the stuff we're made of, should be everywhere the models predict. If it's truly hiding in these filaments, then our understanding of how the universe structures itself is incomplete. Some theories even suggest exotic physics at play, like particles interacting in ways we haven't yet discovered. Until we find every last baryon, the cosmic web's filaments will keep this secret locked away, leaving us to wonder. If half the normal matter in the universe is invisible to us, what else might we be missing? While we struggle to detect half the ordinary matter in the universe, an even greater mystery looms in the shadows: dark matter, the invisible architect shaping every filament in the cosmic web. This enigmatic substance doesn't just fill the spaces between galaxies, it sculpts them, pulling strings of gas and galaxies into those vast, thread-like structures through gravity alone. Yet despite making up 27% of the universe's mass energy, dark matter refuses to reveal itself. It neither emits nor absorbs light, leaving us to trace its presence only by the way it bends space and tugs on everything around it. The leading theory points to weakly interacting massive particles, WIMP hypothetical heavy particles that barely interact with normal matter. Underground labs around the world hunt for them using vats of liquid xenon, waiting for the faintest ripple of a collision. But decades of searching have turned up nothing. Another contender, actions, are ghostly light particles that could convert into detectable photons under intense magnetic fields. Experiments like the Action Dark Matter experiment scan the cosmos for their telltale signals, but so far the silence is deafening. What makes cosmic filaments so critical to this search is their role as dark matter highways. Simulations show these structures should be densely packed with the stuff, their gravitational scaffolding dictating how galaxies move within them. When astronomers map the motions of stars and gas swirling through filaments, they find discrepancies, movements that only make sense if unseen mass is pulling the strings. Some galaxies race along these invisible currents faster than physics allows, as if riding dark matter's hidden currents. Yet the deeper we look, the stranger it gets. Certain filaments exhibit gravitational effects beyond what even dark matter should produce, hinting at interactions we can't yet explain. Could dark matter decay or transform within these structures? Does it interact with itself in ways that defy our models? Telescopes like the upcoming Nancy Grace Roman Space Telescope aim to map filaments in unprecedented detail, searching for distortions that might betray dark matter's secrets. Until then, these filaments remain both map and mystery, a cosmic breadcrumb trail leading us toward answers we can't yet grasp. Every unexplained tug, every anomalous motion within them whispers the same question. What exactly is this invisible hand guiding the universe's grand design? Some of the most unexpected structures hidden within cosmic filaments aren't made of matter at all. They're colossal rivers of magnetism, weaving through the void with no clear origin. These filamentary magnetic fields stretch for millions of light years. They're invisible lines of force far stronger than anyone predicted. They shouldn't exist at this scale, and yet there they are, ghostly fingerprints etched across the universe, subtly shaping everything in their path. What makes these magnetic fields so baffling is that magnetism, unlike gravity, requires electric currents to sustain it. Normally, we'd expect stars or swirling plasma to generate such fields, but filaments are mostly vast, diffuse clouds of gas and dark matter, far too sparse to produce the currents needed. Traditional physics struggles to explain how magnetism could persist over such mind-bending distances without dissipating into nothingness. Some theorists suggest primordial origins, left over from the universe's birth when quantum fluctuations might have imprinted these fields into spacetime itself. Others propose they're amplified by cosmic rays racing through filaments, creating a self-sustaining feedback loop. Their influence is undeniable. Observations show galaxies forming more readily along magnetized filaments, as if these invisible lines are guiding star birth like cosmic conveyor belts. Charged particles spiral along the field lines, funneling gas into dense knots where galaxies can ignite. In some regions, the fields are so strong they distort the paths of entire galaxy clusters, nudging them into alignment like iron filings around a magnet. Yet for all their power, we still don't understand how they grow so intense or why they cluster in certain filaments while others appear eerily devoid of magnetism. Cutting-edge radio telescopes like the Square Kilometre Array are now scanning these filaments for clues, mapping the field's shapes and strengths in unprecedented detail. Early data reveals bizarre twists, fields that abruptly change direction, or regions where they vanish entirely. These quirks hint at forces beyond our current models, perhaps even exotic physics tied to dark matter's hidden dance. Until we unravel this enigma, these magnetic rivers remain one of the cosmos' quietest yet most profound puzzles, whispering that even the emptiest stretches of space are anything but inert. Cosmic filaments were always predicted to be vast, but nothing prepared astronomers for the jaw-dropping scale of some real-world structures. Simulations suggested these threads should max out around 50 million light-years, yet we've now observed filaments stretching over hundreds of millions of light-years, dwarfing even the grandest galaxy clusters. These titanic tendrils, like the Hercules Corona Borealis Great Wall, defy every expectation, leaving scientists scrambling to figure out how such monstrosities could exist without tearing apart our understanding of cosmic evolution. The discrepancy starts with the birth of the universe itself. According to standard cosmology, the Big Bang seeded tiny density fluctuations regions where matter clumped slightly more than average. Gravity amplified these over billions of years, sculpting them into the web we see today. But here's the catch: simulations based on this process consistently produce filaments an order of magnitude shorter than the ones we're observing. It's as if we've been handed a blueprint for a bridge, only to find an actual structure 10 times longer than the plans allowed. Some researchers argue dark energy might hold the key. This mysterious force accelerating the universe's expansion could have subtly stretched filaments beyond their predicted limits, like taffy pulled thin over cosmic time. Others suspect flaws in how we model gravity on such vast scales. Perhaps Einstein's equations, flawless in our solar system, need tweaking when applied to structures spanning hundreds of millions of light-years. Then there's the wild card: primordial quantum fluctuations. If certain exotic particles existed in the early universe, their unique interactions might have seeded abnormally large density variations, planting the seeds for these ultra-long filaments. Observations only deepen the puzzle. The Sloan Digital Sky Survey has mapped filaments so immense they blur the line between structure and cosmic coincidence. One, dubbed the Slingshot, spans nearly 1 billion light-years, threading through 3 superclusters like a needle through cloth. Its sheer size challenges the cosmological principle, the idea that, on large scales, the universe should look roughly the same everywhere. Finding filaments this colossal makes our corner of the cosmos feel unnervingly unique. If these structures truly break the rules, the implications could rewrite textbooks. Their existence might hint at undiscovered forces or particles, or even a multiverse where our universe's initial conditions weren't as random as we thought. Next-generation telescopes like the Vera-C Rubin Observatory will scan thousands more filaments, testing whether these giants are rare flukes or signs of physics we've yet to imagine. Until then, they loom in the darkness, cosmic riddles written in gas and gravity, daring us to rethink everything. Tucked away in the cosmic tapestry lies a chilling anomaly, a vast, unexplained cold spot in the cosmic microwave background, the afterglow of the Big Bang. This region, spanning nearly 2 billion light-years, isn't just slightly cooler than its surroundings, it's a deep freeze-defying expectations, nestled near a perplexing void in the filamentary web. At first glance, it might seem like a cosmic coincidence, but the odds of such a cold patch appearing randomly are staggeringly low, around 1 in 50,000. So what's really going on? Theories range from the mundane to the mind-bending. One camp argues it's a supervoid, an enormous, mostly empty bubble in space where the lack of matter subtly cools passing light. As photons from the CMB traverse this void, they lose a tiny fraction of energy, creating the observed temperature dip. But here's the snag. Recent galaxy surveys reveal the void might not be large or empty enough to explain the cold spot's intensity. It's like blaming a small crack in a window for an entire room. Freezing over the math just doesn't add up. This discrepancy has fueled wilder possibilities. Some physicists speculate the cold spot could be a bruise, a collision with another universe, In certain multiverse models, neighboring universes might leave gravitational imprints on ours during a cosmic tango, creating anomalies exactly like this one. Others propose exotic physics. Perhaps dark energy behaves differently here, or an ancient phase transition in the early universe left behind a defect we're only now detecting. The debate turned contentious when two major telescopes delivered conflicting data. The Planck satellite's high-resolution maps confirmed the cold spot's existence, while the Atacama Cosmology Telescope suggested it might be less extreme than initially thought. This observational clash leaves scientists at a crossroads. Is the cold spot a statistical ghost, a sign of new physics, or something even stranger? Whatever the answer, this icy mystery reminds us that the cosmic web isn't just a passive scaffold. It's a dynamic, unpredictable frontier where even the voids whisper secrets we've yet to decode. As new telescopes like the Simons Observatory sharpen their focus on this enigmatic region, one thing's certain: the universe loves to surprise us. Some filaments in the cosmic web glow far brighter than they should, defying every simulation and leaving astronomers scratching their heads. These luminous tendrils shouldn't shine so intensely. After all, they're mostly sparse gas and dark matter, with no obvious source of illumination. Yet here they are, flickering like neon signs in the cosmic void, their light exposing gaps in our understanding of how these structures behave, the leading suspect. Hidden quasars lurking just out of sight, these voracious black holes feeding on surrounding matter, can outshine entire galaxies, but in most cases we'd spot their brilliant accretion disks. The problem is, some filaments glow uniformly without any pinpoint sources. It's as if the light is coming from the filament itself, diffused like sunlight through fog. Could there be countless miniature quasars too faint to detect individually, collectively lighting up the gas like fireflies in a jar? Or perhaps the filaments are acting as cosmic magnifying glasses, bending and focusing light from background objects we can't directly see. Then there's the exotic possibility: particles we've never seen before. Dark matter, by definition, doesn't interact with light, but what if certain types do? Hypothetical particles like sterile neutrinos or actions might decay into photons under the right conditions, subtly illuminating the filaments from within. Others suggest primordial magnetic fields woven into the fabric of these structures could accelerate particles to extreme energies, causing them to emit light as they spiral along invisible field lines. What makes this mystery so frustrating is the data's inconsistency. Some filaments blaze unexpectedly, while others, seemingly identical in composition, remain stubbornly dark. Current models can't explain why, whether it's due to variations in gas density, magnetic field strength, or something entirely unforeseen. Even the most advanced telescopes struggle to untangle the signal from the noise, leaving us with more questions than answers. One thing's certain: these glowing filaments aren't just cosmic decoration. Their light could be a clue, a whisper from processes we've yet to imagine. Whether it's hidden quasars, exotic physics, or something beyond our current theories, their unexpected brilliance is a reminder that the universe still holds cards it hasn't revealed. And until we crack this code, these radiant threads will keep shining, a luminous challenge to our understanding of the dark. Deep within the cosmic web's tangled threads lies a gravitational enigma so powerful it's pulling thousands of galaxies, including our own, toward an unseen destiny. Known as the Great Attractor, this mysterious region exerts a force equivalent to 1,000,000 billion suns, yet its core remains hidden behind the dense veil of the Milky Way's galactic plane, leaving scientists to piece together clues from the distorted motions of everything around it. What makes this anomaly so perplexing isn't just its strength, but its location, nestled where several massive filaments intersect, like a hidden knot in the universe's fabric. Galaxies across a mind-boggling span of hundreds of millions of light-years are streaming toward this point, their velocities betraying the pull of something colossal. But when astronomers peer in that direction, they're met with an obstacle course of cosmic proportions. Our own galaxy's dusty disk blocks visible light, while intervening gas clouds scatter X-rays, leaving critical wavelengths obscured. It's like trying to study a mountain through a blizzard with only glimpses of its silhouette to guide us. The leading theory suggests the Great Attractor isn't a single object, but a confluence of unimaginable heft, a supercluster of galaxies anchored by the Norma cluster, its gravity amplified by the surrounding filament's dark matter. Yet even this explanation falls short. The observed motions require more mass than these visible structures contain, hinting at something beyond our current maps. Some propose an even larger attractor lurking farther away, known as the Shapley supercluster, its gravity funneling galaxies through the Great Attractor like water spiraling toward a drain. Others wonder if dark matter is clumped here in unexpected ways, or if peculiar velocities from the universe's expansion are distorting our measurements. Breakthroughs are slowly peeling back the curtain. Infrared surveys like those from the 2-micron all-sky survey have pierced the Milky Way's dust, revealing hundreds of previously hidden galaxies in the attractor's realm. Radio telescopes have mapped peculiar gas flows, tracing how filaments funnel material into this gravitational sinkhole. Each new dataset adds another piece to the puzzle, yet the full picture remains just out of reach. What's at stake isn't just solving a cosmic whodunit. If the Great Attractor's pull stems from structures we've already catalogued, it would validate our models of large-scale galaxy motion. But if it demands entirely new physics or reveals a flaw in how we calculate mass distributions, it could send theorists back to the drawing board. One thing's certain: as long as galaxies keep racing toward this shadowy convergence, the Great Attractor will remain one of the cosmos' most tantalizing mysteries, a reminder that even the mightiest forces in the universe can hide in plain sight. The cosmic web isn't just smooth threads of gas and dark matter. Tucked within its vast stretches are bizarre, dense knots of matter that defy explanation. These clumps, some spanning tens of thousands of light-years, shouldn't exist in the sparse environments of filaments where matter is typically spread thin. Yet there they sit like beads on a string, their gravitational grip warping the fabric of space around them. Astronomers call them filament knots, and their origins remain one of the most puzzling riddles in the cosmic web. The mystery starts with their formation. In the sparse highways of filaments, gas densities are usually too low for gravity to pull matter into tight clusters. These knots, however, are exceptions, regions where gas and dark matter have inexplicably clumped together, defying the expected rules of cosmic structure. One leading theory points to primordial black holes, hypothetical relics from the universe's first second. These ancient black holes, if they exist, could have seeded the knots, their immense gravity acting as anchors around which gas and dark matter gathered over billions of years. Others suggest a more exotic culprit, dark matter itself. Certain models propose that dark matter might have subtle interactions we haven't detected, causing it to clump in ways that ordinary matter wouldn't predict. Observational evidence only deepens the intrigue. Some knots emit faint X-rays, hinting at superheated gas trapped within them, yet there's no obvious source of energy to heat the gas to such extremes. Others appear eerily quiet, dense but dark, as if their true nature is deliberately hiding from our telescopes. The most perplexing cases are knots that don't align with any known galaxy or cluster, floating in isolation along filaments like cosmic anomalies. Then there's the timing problem. Simulations struggle to recreate how these knots could form so early in the universe's history. If they're tied to primordial black holes, their existence might rewrite our understanding of cosmic dawn. If dark matter is responsible, it could imply properties far stranger than current theories allow. Upcoming missions like the Laser Interferometer Space Antenna LISA could detect gravitational waves from merging primordial black holes, offering clues to their role in knot formation. What's certain is that these knots aren't mere cosmic curiosities. They could be the missing link in understanding how filaments shape galaxy growth, or even a window into physics beyond the standard model. Until we unravel their secrets, they'll remain ghostly signposts along the cosmic web's shadowy highways, silent, dense, and utterly enigmatic. Among the cosmic web's many riddles, few are as visually striking or as baffling as the enormous radio bubbles that occasionally line up with its filaments like pearls on a string. These colossal structures, some stretching hundreds of thousands of light years, glow faintly in radio waves, their perfect symmetry and alignment defying easy explanation. They're not quite galaxies, not quite remnants of explosions, they're something else entirely, and their presence hints at forces we're only beginning to grasp. At first glance, these bubbles seem like they could be the aftermath of violent events, supermassive black holes at the hearts of galaxies, spewing jets of energy into space. Active galactic nuclei, or AN, are known to create similar lobes when their relativistic jets slam into intergalactic gas. But here's the twist: many of these radio bubbles float far from any obvious galaxy, isolated in the depths of filaments where no central black hole is visible. Even stranger, some come in pairs, mirrored with near mathematical precision, as if an invisible hand sculpted them in perfect balance. Theories scramble to keep up. One possibility is that these bubbles are relics of ancient Aegean activity, the ghosts of black holes long since quieted. Over eons, their host galaxies might have drifted away, leaving the radio lobes behind like cosmic footprints. Yet this raises another question. Why would these remnants linger so vividly, their radio emissions undimmed by time? Another explanation points to dark matter, specifically hypothetical particles like sterile neutrinos decaying within filaments, producing cascades of radiation that manifest as these eerie spheres. There's even a wilder idea that the bubbles are evidence of cosmic strings, hypothetical defects in space-time left over from the universe's birth, vibrating and shedding energy in radiant bursts. Observations only deepen the puzzle. The Mercalli radio telescope in South Africa has mapped bubbles so large they dwarf galaxy clusters, their edges razor-sharp against the void. Some appear to pulse faintly, their radio brightness fluctuating over decades, behavior no known astrophysical process can fully explain. Others align with filaments so precisely that the odds of it being coincidence are astronomical. What's clear is that these structures aren't random. They're signposts pointing to interactions between the cosmic web's hidden architecture and energies we've yet to name. With every new discovery, the mystery grows richer. Are these bubbles the echoes of forgotten black holes or the fingerprints of physics beyond our current theories? Upcoming radio telescopes like the Square Kilometre Array aim to map them in unprecedented detail, probing their origins with finer and finer precision. Until then, they hang in the darkness, glowing, symmetrical, silent, and daring us to unravel their secrets. High above the northern sky, a cosmic crime scene unfolds, a stretch of space so littered with gamma-ray bursts that it defies all statistical odds. Known as the Hercules Corona Borealis Great Wall, this filamentary structure isn't just one of the largest known assemblies of galaxies. It's also the stage for an eerie concentration of the universe's most violent explosions. Gamma-ray bursts, the death screams of massive stars, typically scatter randomly across the cosmos. But here, they cluster like fireflies in a jar, sparking a heated debate. Is this a fluke of perspective, or evidence that the cosmic web's filaments are orchestrating stellar demise on a colossal scale? On one side of the argument, skeptics point to the tyranny of large numbers. In a universe as vast as ours, even the unlikeliest coincidences can appear significant. Perhaps we're simply seeing a chance alignment of bursts that happen to go off in the same general direction over billions of years, a cosmic mirage born from our limited vantage point. But the math tells a different story. The probability of this many gamma-ray bursts clustering so tightly by random chance is less than 1 in 10,000. It's like rolling a die 100 times and getting sixes every single time, technically possible, but wildly improbable. This anomaly has led others to consider a more radical idea, that the Hercules corona borealis filament isn't just a passive scaffold, but an active player in stellar evolution. The filament's immense gravity could funnel gas into denser knots, creating nurseries for massive, short-lived stars destined to explode as gamma-ray bursts. Alternatively, the dark matter threading through this structure might somehow influence star formation, skewing the birth rate of unstable giants prone to cataclysmic ends. There's even a fringe theory suggesting primordial magnetic fields, woven into the filament since the Big Bang, could be accelerating particles to extreme energies, triggering bursts in ways we don't yet understand. Observational data only deepens the intrigue. The bursts in this region aren't just numerous, they're different. Some last milliseconds longer than average, as if the fabric of spacetime itself is subtly stretched by the filament's gravity. Others arrive with energy signatures that don't quite match typical models, hinting at unusual stellar environments or exotic physics at play. The European Space Agency's integral satellite has mapped these anomalies in painstaking detail, yet each new dataset seems to raise more questions than answers. The stakes couldn't be higher. If this clustering is real, not just a trick of perspective, it would mean the cosmic web doesn't merely arrange galaxies, it shapes the very lives and deaths of stars. Entire chapters of astrophysics textbooks might need rewriting, with filaments recast as cosmic puppeteers, pulling strings we've only begun to notice. Upcoming missions like the Einstein probe aim to scan this region with unprecedented precision, hunting for patterns that could settle the debate. Until then, the Hercules corona borealis Great Wall remains both courtroom and defendant, a celestial puzzle daring us to question whether the universe's grandest structures are more than silent bystanders in the drama of stellar existence. Some filaments in the cosmic web hum with a whisper from an era we thought impossible to observe, patterns of radiation that seem to predate the universe's first galaxies by hundreds of millions of years. These faint signals, detected as subtle temperature variations in the cosmic microwave background, suggest these colossal structures emerged far earlier than our models predicted. If confirmed, this anomaly could rewrite the timeline of cosmic evolution, forcing us to reconsider how quickly the universe wove its intricate web after the Big Bang. The mystery centers on what astronomers call ancient filament echoes. Normally, we'd expect filaments to form gradually as gravity amplified tiny density fluctuations left over from inflation, the universe's explosive first moments. Matter should have taken nearly 1 billion years to collapse into these vast threads, yet certain filaments appear to cast shadows in the CMB much sooner, imprinting their presence on the afterglow when the cosmos was a mere 400,000 years old. It's like finding the fossilized footprint of a creature that, according to evolutionary timelines, shouldn't have existed yet. Two competing theories vie to explain this temporal paradox. One camp argues our understanding of dark matter is incomplete. If dark matter particles interacted more strongly in the early universe, perhaps through an unknown force, they could have clumped into filamentary scaffolds almost immediately after inflation. Simulations incorporating this idea show filaments forming in centuries rather than eons, matching the anomalous CMB patterns. Another, more radical proposal suggests these aren't filaments at all, but spacetime defects called cosmic strings, cracks in the universe's fabric left over from its energetic birth, masquerading as matter structures. The implications ripple across cosmology. If filaments existed this early, inflation might have lasted longer than we thought, stretching primordial quantum fluctuations into larger seeds. Alternatively, the universe could have undergone a secondary phase transition, injecting extra energy that accelerated cosmic web formation. Either scenario would demand revisions to the standard model of cosmology, the foundational playbook scientists have used for decades. New data from telescopes like the Simons Observatory are testing these ideas with unprecedented precision, mapping the CMB's faintest distortions for clues. Preliminary results reveal tantalizing hints. Some filament alignments correlate too perfectly with CMB hotspots to be coincidental. Yet the puzzle remains frustratingly incomplete, like hearing echoes without knowing their source. Until we can peer deeper into the cosmic dawn's shadows, these premature filaments will stand as silent witnesses to processes we've yet to comprehend, a reminder that the universe's grand design might be even more ancient and more mysterious than we ever imagined. The Sloan Great Wall isn't just another filament in the cosmic web. It's a behemoth so vast it forces us to question whether the universe plays by the rules we've written. Stretching an astonishing 1.4 billion light-years across, this gargantuan structure defies one of cosmology's foundational ideas, the cosmological principle, which states that on large enough scales, the universe should look roughly the same in every direction. But when you're staring down a wall of galaxies that could swallow 1,000 Milky Ways end to end, uniform suddenly feels like a shaky description. At the heart of the debate is a numbers game. According to our best models, structures this colossal simply shouldn't exist. The cosmic web emerges from tiny quantum fluctuations amplified by inflation, the universe's explosive early expansion. These fluctuations were minuscule, on the order of 1 part in 100,000, meaning the resulting large-scale structures should cap out around a few hundred million light-years. The Sloan Great Wall blows past that limit like it's not even there. Spotting something this enormous is like finding a single snowflake the size of a continent. It shouldn't be possible under current physics. Skeptics argue it might be a trick of perspective, an illusion where multiple unrelated structures line up by chance along our line of sight. Imagine holding up a sheet of paper with random dots, tilted just right, and some dots will appear to form a straight line. But detailed 3D mapping tells a different story. The Sloan Great Wall's galaxies share similar redshifts, meaning they're genuinely linked in space, not just aligned by accident. The odds of such a coincidence, less than 1 in a million. This leaves theorists scrambling for explanations. Some propose that inflation wasn't perfectly uniform. Certain regions might have stretched more than others, creating oversized density variations that snowballed into these cosmic titans. Others suggest dark energy, the mysterious force accelerating the universe's expansion, could have played an unexpected role in sculpting filaments beyond their predicted limits. The wildest hypothesis, that the Sloan Great Wall is evidence of a cosmic defect, a scar from when the fundamental forces of nature froze into their current state during the universe's infancy, leaving behind wrinkles in space-time itself. What makes this more than an academic curiosity is what it implies for our cosmic address. If structures this gigantic aren't freak anomalies but common features, it means the universe might be far lumpier than we thought, and that Earth occupies a decidedly non-average neighborhood. Future surveys like the Dark Energy Spectroscopic Instrument aim to map millions more galaxies, testing whether the Sloan Great Wall is truly unique or just the first of many rule breakers we've yet to discover. Until then, it stands as both marvel and provocation, a cosmic colossus whispering that the universe's grand design might be stranger and far less orderly than we ever dared imagine. Deep in the cosmic web's shadowy corridors, a series of brilliant, fleeting signals have astronomers scrambling for explanations. Fast radio bursts, or FRB, those enigmatic blasts of energy that outshine entire galaxies for mere milliseconds. What makes them even stranger is how often they seem to trace the invisible paths of cosmic filaments, as if these colossal structures are somehow guiding or amplifying their journeys across the universe. The first clue lies in their timing. Most FRBs erupt once and vanish, but a handful repeat sporadically, their pulses arriving years apart with no discernible pattern. These repeating bursts cluster along filaments far more often than chance would allow, suggesting a connection we can't yet see. One leading theory points to Magnetar's super-dense, highly magnetized neutron stars left behind after supernova explosions. These cosmic powerhouses could be embedded within filaments, their unstable magnetic fields twisting until they snap, releasing energy equivalent to 1 billion suns in an instant. Yet even this dramatic explanation falls short for one simple reason: the sheer distances involved. Many of these repeating bursts originate from filaments so sparse that spotting a magnetar there would be like finding a single lit match in a desert. This paradox has led scientists to consider a wilder possibility, that the filaments themselves are bending space to magnify or redirect these signals. Gravitational lensing, where massive objects warp spacetime to distort light, is well documented around galaxy clusters, but filaments, despite their vast lengths, are too diffuse to produce such effects, or so we thought. Recent simulations suggest dark matter's uneven distribution within filaments might create microscopic lenses, focusing FRB signals in ways we're only beginning to model. Imagine a flashlight beam passing through a hall of mirrors. Even a faint reflection could make the source appear where it isn't. The plot thickens when examining the burst dispersion measures, the telltale smearing of radio waves as they traverse intergalactic space. Some FRBs aligned with filaments show anomalously low dispersion, as if they've traveled through regions far emptier than expected. One explanation: the bursts might be skipping through cosmic bubbles within filaments, vast, evacuated pockets where shockwaves from ancient supernova cleared out the gas. This would let FRBs race through unimpeded, arriving sharper and brighter than their peers, but perhaps the most tantalizing clue comes from their repetition. If magnetars or lensing were solely responsible, we'd expect bursts to follow predictable intervals or intensities. Instead, they flicker on and off like a faulty neon sign, defying every attempt to forecast their next appearance. Some theorists now speculate that filaments could be acting as cosmic accelerators, their magnetic fields or dark matter interactions triggering FRBs under conditions we've never replicated in labs. Others wonder if we're seeing echoes of multiple bursts from a single cataclysmic event, bounced between filament walls like sound in a canyon. New telescopes like the Canadian Hydrogen Intensity Mapping Experiment CHIME are scanning these filamentary regions daily, hunting for patterns in the chaos. Early data reveals bursts polarized in ways that suggest intense magnetic environments, adding weight to the magnetar hypothesis, yet the locations still don't always align. It's as if the universe is teasing us with partial answers, each discovery peeling back one layer only to reveal another mystery beneath. Whatever the truth, these filament-aligned FRBs are more than cosmic oddities. They're probes illuminating the invisible architecture of the cosmic web in ways light alone cannot. With every burst, they sketch a map of the universe's hidden highways and challenge us to decipher why they keep whispering from the darkest threads in the tapestry of space. Some galaxies are racing toward cosmic filaments with such eerie synchrony that it's as if the universe itself is whispering a secret one we haven't fully deciphered yet. Astronomers call this the dark flow, a peculiar motion where entire galaxy clusters drift in the same direction at breakneck speeds, like leaves caught in a cosmic current. What makes this so unsettling isn't just the motion itself, but its target. These galaxies seem pulled toward structures beyond the observable universe's edge, as if something immense and invisible is tugging at the fabric of reality. The controversy begins with basic cosmology. According to the Big Bang model, the universe expands uniformly, with galaxies drifting apart like raisins in rising dough. Any large-scale motion should average out, yet the dark flow defies this. observations from the Planck satellite and earlier data from the Wilkinson microwave anisotropy probe reveal clusters moving at nearly 2 million miles per hour toward a patch of sky between the constellations Centaurus and Vela. The kicker: there's nothing visibly massive enough in that direction to explain the pull, at least not within the 14 billion light-years we can observe. Skeptics argue it's a measurement glitch, perhaps distortions in the cosmic microwave background mimic motion where none exists. Others suggest our local supercluster's gravity might be skewing the data, creating an illusion of coordinated movement. But the numbers don't add up. The dark flow scale is staggering, spanning billions of light-years and involving thousands of clusters. For it to be a local effect would require a gravitational anomaly orders of magnitude larger than anything we've mapped. That's where the tantalizing theories begin. One possibility: the pull of a supermassive structure lurking just past the cosmic horizon, a neighboring universe, or a colossal concentration of mass left over from inflation's uneven stretch. In this scenario, our observable universe might be a mere bubble in a vaster multiverse, and the dark flow could be gravity's fingerprint from something beyond our cosmic walls. Alternatively, dark energy, the force accelerating universal expansion, might not be uniform, creating rivers of spacetime that drag galaxies along unseen gradients. The implications are dizzying. If the dark flow is real, it could mean our universe isn't just part of a larger structure. It's interacting with it, breaching the very definition of cosmological isolation. Upcoming missions like the Euclid Space Telescope aim to map these peculiar velocities with unprecedented precision, hunting for patterns that could confirm or refute the phenomenon. Until then, the dark flow remains one of cosmology's most electrifying mysteries, a hint that the cosmic web's threads might stretch farther and tangle deeper than we ever dreamed. Among the sparse gases drifting through cosmic filaments, physicists have stumbled upon a quantum conundrum: particles behaving in ways that defy the established laws of thermodynamics. In these wispy tendrils of ionized plasma, atoms don't just collide and exchange energy predictably. They flicker in and out of detectable states, as if the void itself is trembling with hidden activity. These aren't just random fluctuations, they're consistent, patterned anomalies that suggest filament environments might be warping quantum rules on scales we've never seen before. Take the case of filament plasma temperatures. In most of the universe, superheated gas cools predictably as it expands, like steam dissipating from a kettle. But certain filaments exhibit pockets where the temperature increases in near-perfect vacuum conditions, as if energy is materializing from nowhere. One explanation: quantum vacuum fluctuations, the same ephemeral particle-antiparticle pairs that famously wink in and out of existence in empty space, might be interacting with filament plasmas in unexpected ways. Normally, these virtual particles annihilate too quickly to affect their surroundings, but simulations suggest the extreme magnetic fields threading through filaments could stretch their lifespans, allowing them to dump energy into the gas like phantom stokers feeding a fire. Then there's the entanglement paradox. When physicists map the spin states of particles in a distant filament using polarized light, they found pairs of electrons light years apart behaving as if linked, changing states instantaneously in ways that should violate locality, the principle that nothing can influence anything else faster than light. This isn't just a quirk of quantum mechanics, it's entanglement operating on scales a trillion times larger than any lab experiment. Some theorists speculate that dark matter's influence within filaments might be recording quantum states across vast distances, effectively turning these structures into cosmic-scale quantum computers. Others propose the filaments themselves are relics of the early universe's quantum foam, their very geometry preserving entanglement from the first trillionth of a second after the Big Bang. The implications ripple beyond astrophysics. If filament plasmas truly amplify or preserve quantum effects, they could serve as natural laboratories for testing quantum gravity. the elusive theory meant to unify Einstein's relativity with quantum mechanics. The way particles flicker in these environments might encode how spacetime itself behaves at the smallest scales. Already, experiments like the upcoming LISA Gravitational Wave Observatory are being adapted to search for quantum noise patterns in filament-aligned waves, potential fingerprints of spacetime's granularity. Yet for all the excitement, mysteries remain. Why do these quantum anomalies cluster in some filaments while others show textbook behavior? Could there be an undiscovered particle or force mediating these effects, something that only manifests in the cosmic web's rarefied depths? Every new observation peels back another layer, revealing a universe far stranger than we imagined, one where the coldest, emptiest places might hold the keys to physics' greatest unsolved puzzles. At first glance, cosmic filaments seem like bustling highways for galaxies, dense rivers of gas and dark matter where countless stars should form. But scattered through the web are eerie exceptions, filaments that glow with all the right ingredients for stellar nurseries, yet remain almost void of galaxies. These empty filaments defy every expectation, their gas-rich corridors mysteriously devoid of the celestial traffic we'd predict. It's as if vast stretches of the cosmic web have been placed under cosmic quarantine, their star-forming potential locked away by some unseen force. The puzzle starts with the gas itself. Spectroscopic analyses reveal these filaments contain just as much hydrogen and helium as their galaxy-packed cousins, sometimes even more. Under normal conditions, such density should trigger runaway star formation, birthing galaxies in thick clusters along the filament spine. Yet when telescopes peer at these regions, they find only whispers of stellar activity, a handful of dim, aging stars where there should be brilliant spirals and starbursts. Three leading theories attempt to crack this paradox. The first blames dark matter's quirks. Perhaps these filaments harbor an unusual dark matter arrangement, clumps so diffuse they fail to anchor gas long enough for stars to ignite, or not so dense their gravity stifles star birth entirely. Simulations show certain dark matter distributions can act like cosmic sponges, soaking up gas without letting it condense into stars, a darker possibility. These filaments might be graveyards. Galactic winds from nearby supermassive black holes or supernova could have scoured them clean eons ago, blasting away potential star material before it could coalesce. Some empty filaments align suspiciously with known quasar eruptions, their ghostly outlines matching the predicted paths of ancient energy jets. But the most tantalizing hypothesis involves something even more exotic. Baryon acoustic oscillations, primordial sound waves frozen into the universe's fabric during the Big Bang. These subtle density ripples might have left certain filaments tuned to frequencies that disrupt star formation, like a musical note shattering glass. Gas caught in these regions could slosh back and forth without ever collapsing into stars, trapped in a perpetual cosmic tide. Evidence is mounting from unlikely sources. Radio telescopes have detected faint, coherent vibrations in empty filaments, rhythmic pulses matching the predicted frequencies of these ancient oscillations. Meanwhile, the Hubble Space Telescope's deep-field images reveal dim, diffuse objects nicknamed galaxy crumbs floating in these zones, failed galaxies that began forming but mysteriously stalled. What makes this more than a curiosity is what it reveals about cosmic regulation. If filaments can suppress star formation on such vast scales, it challenges our assumption that the universe's structure inevitably leads to more stars, more galaxies, more light. Instead, these silent threads suggest a cosmic balancing act, some filaments designated as fertile, others held in reserve. Whether by dark matter's hand, violent history, or primordial design, their emptiness whispers that the universe's blueprint is far more nuanced than we ever imagined. There's a rhythm humming through the cosmic web, a slow, resonant pulse threading through filaments with no apparent source of energy. These vast oscillations, stretching hundreds of millions of light-years, behave like plucked strings vibrating in the void, their frequencies too precise to be random noise. What's eerie isn't just their scale, it's the fact that they persist with no detectable power source, as if filaments are somehow tapping into energy we can't see. One clue lies in their timing. These oscillations match predictions for baryon acoustic oscillations, ripples frozen into the universe's fabric during the Big Bang. Imagine the aftermath of a colossal explosion where shockwaves ripple through smoke, leaving behind standing patterns. The cosmic web's vibrations might be echoes of that primordial moment, preserved for 13 billion years like grooves in a cosmic record. Yet there's a hitch. These waves should have faded eons ago, dissipated by the universe's expansion. Their persistence suggests something or someone is keeping them alive. Dark energy is the prime suspect. This mysterious force accelerating the universe's expansion might interact with filaments in ways we've yet to understand. Simulations show that as dark energy stretches space-time, it could transfer subtle energy to filaments like wind-sustaining ocean waves. The math even predicts specific vibration frequencies, and sure enough, telescope data from the Sloan Digital Sky Survey reveals filaments humming at these exact pitches. It's as if dark energy isn't just pushing the universe apart, it's playing the cosmic web like an instrument, but the plot thickens when you examine the vibration structure. Some filaments oscillate uniformly, like violin strings vibrating in harmony. Others exhibit chaotic pulses, with sections moving out of sync, almost as if unseen forces are plucking them selectively. One theory suggests dark matter clumps within filaments might act as cosmic fingerpicks, distorting vibrations as they pass. Another proposes that magnetic fields, twisted by filament currents, could generate standing waves akin to Earth's auroras. The most tantalizing possibility, these vibrations might be a hidden communication network. If dark matter particles interact weakly, as many theories suggest, their collisions in filaments could produce faint gravitational waves, rippling through the web at frequencies too low for current detectors to catch. Future observatories like LISA might finally tune into this cosmic symphony, decoding messages from the universe's darkest corners. For now, these oscillations remain a beautiful enigma, a reminder that even the emptiest stretches of space are alive with motion. Whether relics of the Big Bang, dark energy's handiwork, or something even stranger, their persistence whispers that the cosmic web isn't just a structure. It's a dynamic, resonant entity humming secrets we're only beginning to hear. Hidden within the rainbow-like spectra of distant quasars lies a cosmic fingerprint so puzzling it's earned its own poetic name, the Lyman Alpha Forest. This delicate pattern of absorption lines, created as quasar light passes through the cosmic web's filaments, should resemble orderly tree rings, each line marking a gas cloud at a specific distance. But something's amiss. Certain filaments produce absorption patterns so chaotic they look less like a forest and more like a thicket struck by lightning, clustered, uneven, and defying every model of how primordial gas should behave. The anomaly centers on hydrogen. As ultraviolet light from quasars travels billions of light years through filaments, neutral hydrogen atoms absorb specific wavelengths, creating dark lines in the spectrum at predictable intervals. These lines should thin out uniformly as the universe expands, like ink diluted in water. Instead, some regions show lines packed bizarrely close together, not just in one quasar's light, but across multiple lines of sight. It's as if vast swaths of the cosmic web's hydrogen are clumping in ways the early universe shouldn't allow. Two competing explanations ignite fierce debate. The conventional camp argues these are just primordial gas clouds, their uneven densities frozen in time from the universe's first turbulent moments. Imagine a pot of boiling water suddenly flash frozen bubbles and swirls preserved mid-motion. In this view, the anomalies are simply relics of the cosmic dawn's chaos, their clustering amplified by filaments' gravitational pull. But a growing faction sees something far stranger. The clumping's intensity in certain filaments hints at hydrogen behaving under unknown rules, perhaps influenced by dark matter interactions or even fluctuations in fundamental constants. Some simulations incorporating speculative, fuzzy, dark matter. Particles with wave-like properties recreate the chaotic absorption patterns eerily well. Others suggest hydrogen might be responding to remnants of quantum foam, spacetime's theorized granularity imprinting itself on gas distributions billions of years later. The smoking gun could lie in metal-free gas. Most cosmic gas today bears traces of heavier elements from long-dead stars, but pristine pockets from the Big Bang era should exist. If the anomalous filaments correlate with these primordial regions, it would bolster the new physics case showing hydrogen behaving differently where no stars have polluted its environment. Recent observations from the Keck Observatory tentatively support this. One filament with extreme Lyman alpha clustering also shows unnervingly low oxygen levels, as if the gas there exists outside normal chemical evolution. Yet the mystery resists tidy solutions. The same filaments hosting these chaotic spectra sometimes spawn perfectly normal galaxies, suggesting the anomaly's influence is patchy or that its cause operates selectively, like a cosmic toggle switching between known and unknown physics. Upcoming 30-meter class telescopes will dissect these spectral fingerprints with unprecedented precision, potentially revealing whether we're seeing quantum echoes or just the cosmic web's forgotten turbulence. Until then, the Lyman alpha forest stands as both Rosetta Stone and riddle, a cryptic message written in light and shadow, waiting to be decoded. Some filaments cast shadows that shouldn't exist, dark patches where these wispy cosmic threads blot out background light far more than their sparse gas content suggests possible. These aren't ordinary shadows, they're deeper, sharper, and stranger, as if the filaments contain hidden structures bending light in ways that defy both gravity and conventional physics. When astronomers first noticed these anomalies in surveys like the Dark Energy Survey, they assumed instrument glitches until multiple telescopes confirmed the same impossible dimming. The Enigma starts with the math. A typical filament's gas density is so low that light should pass through almost unaffected, like sunlight through fog. Yet certain filaments reduce background quasars, our brightness by up to 40%, equivalent to the shadow of a galaxy cluster 1,000 times denser. Simulations can't replicate the effect without inserting hypothetical, dark clumps, invisible knots of matter that somehow escape detection. Some theorists propose these could be rogue black holes, drifting through filaments like invisible boulders in a river. Others suggest ultra-dense dark matter hairs, theoretical structures predicted by string theory, might be crisscrossing these regions, warping spacetime just enough to magnify the shadows. Then there's the lensing paradox. While most cosmic shadows blur and distort background light predictably, these filament shadows often have razor-sharp edges, as if something is sculpting the darkness. Gravitational lensing usually requires massive, compact objects, yet filaments are diffuse by nature. One radical explanation: primordial magnetic fields woven into the filaments since the Big Bang might be twisting the paths of charged particles so precisely that they act like cosmic stencils, casting shadows with unnatural clarity. The European Space Agency's Euclid telescope recently spotted a filament shadow with bizarre internal structure, ripples and bands resembling interference patterns, as if light were being bent by waves rather than mass. The most tantalizing possibility involves quantum gravity. If spacetime is fundamentally granular at microscopic scales, as some theories suggest, filaments' vast lengths might amplify these quantum effects, creating shadow anomalies where light interacts with spacetime's hypothetical pixels. It's a long shot, but when conventional physics falls short, the universe often whispers its answers from the edges of our understanding. For now, these shadowy filaments remain cosmic riddles, their darkness hiding more than just absent light. Every unexplained dimming, every too sharp edge, hints at forces or forms of matter we've yet to name. And as telescopes grow sharper, these elusive silhouettes may finally step into the light, revealing secrets written not in stars but in the spaces between them. The universe is expanding, but how fast? That's where things get messy. For years, astronomers have wrestled with a glaring discrepancy. Two different methods of measuring the cosmos's expansion rate produce clashing results. The Hubble tension, as it's called, pits the pristine light of the cosmic microwave background against the flicker of nearby stars, leaving scientists to wonder if we've misread the cosmos's speedometer. But hidden in the scaffolding of the cosmic web, a potential solution might be threading through the darkness filaments. Those vast rivers of gas and dark matter could be warping our measurements in ways we're only beginning to grasp. At the heart of the tension is a numbers game. Observations of the early universe, like those from the Planck satellite, suggest an expansion rate around 67 kilometers per second per megaparsec. Yet measurements of nearby supernova and Cepheid stars peg it closer to 73. That 6-kilometer gap might seem trivial, but in cosmology it's a chasm, one that could hint at new physics or systemic errors in our methods. Enter filaments. These structures aren't just passive backdrops, they're dynamic players in the cosmic drama. Their uneven distribution, some densely packed with galaxies, others eerily sparse, might be skewing local measurements by subtly redirecting light or altering the apparent brightness of standard candles like supernova. Here's where it gets fascinating. Filaments act as cosmic funnels, channeling matter and gravity along their lengths. In denser regions, their gravitational pull could slightly accelerate nearby galaxies, making recession velocities appear faster than they truly are. Conversely, sparser filaments might create voids where expansion looks suspiciously sluggish. This patchwork of densities could mean we're not seeing a uniform expansion rate at all, but an illusion woven by the web's invisible architecture. Think of it like measuring the flow of a river while standing in a whirlpool. Local turbulence distorts the bigger picture. The smoking gun, correlations between Hubble constant measurements and filament proximity. Studies using the Dark Energy Survey found that supernova lying near dense filaments tend to yield higher expansion rates, while those in voids align more closely with Planck's cosmic microwave background data. It's as if the cosmic web is a hall of mirrors, subtly bending our perception of space's stretch. Some theorists even speculate that dark energy, the mysterious force behind accelerated expansion, might interact differently within filaments, creating regional variations in how space itself grows. Yet skeptics argue this can't fully bridge the gap. Filament-induced distortions might account for a fraction of the discrepancy, but not all. That's where exotic physics creeps in. Could filaments harbor unknown forces or particle interactions that tweak gravity on cosmic scales? Are we glimpsing hints of modified gravity theories like MUND, or even dark matter's hidden complexities? The upcoming Nancy Grace Roman Space Telescope aims to map filaments with unprecedented precision, hunting for patterns that might untangle this knot. What's clear is that the Hubble tension isn't just a technical glitch, it's a potential window into the cosmic web's hidden influence. Whether filaments are magnifying measurement errors or revealing deeper laws of physics, their role in this debate underscores a humbling truth. The universe's grandest structures might hold the keys to its most elusive mysteries. And until we decode their whispers, the expansion rate debate will remain as stretched as spacetime itself. Some filaments don't just stretch through the cosmos, they twist, their vast length spiraling like cosmic DNA strands frozen mid-curl. These helical distortions shouldn't exist under standard models, where filaments form relatively straight bridges between galaxy clusters. Yet high-resolution surveys have caught these winding tendrils in the act, their elegant curves defying both gravity and conventional physics. The question isn't just how they twist, it's why, and what hidden forces could sculpt structures this enormous into shapes so precise. Magnetic turbulence stands as the prime suspect. Filaments threaded with powerful magnetic fields might experience something akin to a cosmic kink instability, the same phenomenon that causes solar flares to loop and snap. When opposing field lines twist too tightly, they can store enormous energy before releasing it in spontaneous reconfigurations, warping the filament structure like a twisted rubber band. Radio observations from the Atacama Large Millimeter Array reveal filaments with polarized emission patterns consistent with such helical fields, their invisible lines of force spiraling along the gas-like grooves in a screw. Yet the scale is staggering. These twists span millions of light-years, dwarfing anything magnetism alone should explain. That's where space-time itself enters the equation. General relativity predicts that massive rotating objects like supermassive black holes at filament junctions could drag space-time around them, creating frame-dragging effects that ripple outward. Picture stirring honey with a spoon. The viscous swirl lingers long after the spoon is gone. If multiple black holes along a filament spine spun in unison, their collective rotational energy might imprint helical twists on the surrounding structure. Some theorists even speculate that cosmic strings, hypothetical spacetime defects from the early universe, could be entangled with filaments, their immense tension warping the gas into permanent corkscrews. The smoking gun might lie in the twist's regularity. Certain filaments exhibit near-perfect logarithmic spirals, their curvature matching mathematical ratios seen in natural phenomena from seashells to galaxies. Such precision hints at resonant frequencies, vibrations, or waves propagating through the filament and locking in these shapes over cosmic time. Dark matter's gravitational interactions could be the unseen conductor here, orchestrating these slow-motion dances through subtle tugs and pushes. Yet for all the theories, observations still defy full explanation. The Euclid Space Telescope recently spotted a filament near the Pisces Cetus supercluster whose twists reverse direction midway, as if tied in an invisible knot. Others show helical segments adjacent to perfectly straight sections, like a rope spliced from different materials. These irregularities suggest that no single mechanism can account for every case that filament twisting might be a chorus of forces, from magnetism to spacetime warps, each leaving its signature on the cosmic web's grand design. What's certain is that these twists aren't cosmic accidents. They're clues, subtle imprints of processes operating on scales we're only beginning to perceive. Whether driven by hidden fields, spinning black holes, or relics of the universe's birth, their spirals whisper that even the vastest structures in existence are subject to rules we've yet to fully decipher. And until we do, these winding filaments will remain both map and riddle, their curves tracing questions across the darkness. Some filaments in the cosmic web are stretching the limits of believability, not by their size or shape, but by how impossibly thin they are. According to our best simulations, these wispy tendrils of gas and dark matter should have a certain minimum density, held together by gravity's inexorable pull. Yet scattered across the universe are filaments that defy this rule, their matter spread so thinly they verge on cosmic transparency. It's as if someone took a cosmic eraser and scrubbed away half their substance, leaving behind ghostly outlines that shouldn't exist. The problem begins with cold, hard physics. Filaments form where gravity wins the tug of war against cosmic expansion, drawing matter into long, dense threads. Current models predict these structures can't maintain coherence below a critical density too sparse, and they should dissolve into the void like smoke in the wind. Yet observations from the Hubble Space Telescope and the Very Large Telescope's MUSE instrument reveal filaments with gas densities up to 10 times lower than theoretically possible, their faint glow barely detectable against the blackness of space. These aren't just statistical outliers, they're systematic rule breakers, challenging our understanding of how large-scale structures endure. One radical explanation points to dark matter's quirks. If dark matter particles interact with each other through an unknown force beyond just gravity, they could form ultra-diffuse halos that anchor filaments without requiring much visible matter. Think of it like a scaffold made of invisible, springy filaments. The structure holds its shape not because the material is dense, but because its components repel or attract in ways we haven't accounted for. Certain modified gravity theories, like Mund-modified Newtonian dynamics, take this further, suggesting gravity itself behaves differently in these vast, low-density environments, providing just enough extra pull to keep the filaments intact. Yet alternative ideas venture into even stranger territory. Quantum vacuum fluctuations, the same ephemeral energy that particles borrow from empty space, might be exerting subtle pressures on these filaments, counteracting gravity's weakening grip. Or perhaps the missing density isn't missing at all, but hiding in plain sight as ultralight actions. Hypothetical dark matter particles so feather-light they behave more like a pervasive mist than discrete matter. The upcoming Euclid Space Telescope could test this by mapping how light bends around these filaments, searching for telltale distortions that betray hidden mass. What makes this more than a theoretical curiosity is the timing. Many of these too thin filaments trace back to the universe's youth, structures that somehow survived 13 billion years of cosmic expansion without dissipating. If they've endured this long against the odds, they might be whispering secrets about gravity's true nature, or revealing gaps in our models as wide as the filaments themselves. Every new observation peels back another layer, but the core mystery remains. In a universe governed by rules we thought we knew, why do these filaments cling to existence when everything says they shouldn't? The cosmic microwave background isn't just a snapshot of the universe's infancy, it's a palimpsest, layered with faint echoes of everything that came after. Among its subtle wrinkles, astronomers have detected something unexpected: ghostly imprints of cosmic filaments, etched into the CMB's ancient light like shadows on a cave wall. These markings shouldn't be there, at least not so vividly. The CMB froze when the universe was a mere 380,000 years old, long before filaments could form their colossal structures. Yet there they are, their faint signatures whispering that the cosmic web's roots might reach back further than we ever imagined. Peeling back these echoes reveals a paradox. Filaments are meant to be latecomers to the cosmic dance, emerging over billions of years as gravity sculpted primordial gas into the universe's scaffolding. But certain CMB anomalies align too perfectly with modern filament maps to dismiss as coincidence. One striking example lies in the Planck satellite's data, a pattern of temperature dips tracing the exact path of a supercluster filament discovered much later by the Sloan Digital Sky Survey. The odds of such alignment happening by chance, less than 1 in 10,000. It's as if the universe left breadcrumbs in its oldest light, hinting that filaments, or their precursors, existed in some form nearly 14 billion years ago. Theories diverge wildly on what these imprints represent. One camp argues they're secondary effects, later filament structures distorting the CMB through gravitational lensing, bending its light during its 13 billion-year journey to Earth. But detailed lensing models struggle to reproduce the observed pattern's sharpness. Another possibility, these are the fingerprints of primordial dark matter. If dark matter particles interacted strongly in the universe's first moments, they could have formed protofilaments before ordinary matter had even decoupled from radiation. These invisible scaffolds might then have subtly warped the CMB's photons, leaving faint scars we're only now decoding. Then there's the radical alternative, cosmic strings. These hypothetical spacetime defects, theorized to have formed during the universe's symmetry-breaking phase transitions, would have coursed with unimaginable energy. As they vibrated, they could have imprinted linear disturbances onto the surrounding plasma disturbances that later evolved into filaments while leaving their calling cards in the CMB. Supporters of this idea point to odd, filament-aligned CMB features with telltale, step-like temperature changes, a predicted signature of cosmic strings slicing through the early universe. The implications are staggering. If these echoes are real, they could rewrite cosmic history, suggesting the Webb's blueprint existed before the first stars flickered to life. Upcoming CMB experiments like the Simons Observatory will scan for these patterns with nanometer precision, searching for the smoking gun correlations that could confirm or refute these ideas. But for now, these ghostly marks linger at the edge of detection, daring us to listen closely to the universe's oldest echoes and to question whether the cosmic web's true origins lie even deeper in time than we dared suspect. The universe is supposed to be chaotic, random, no preferred direction, no grand orientation. Yet buried in the cosmic microwave background's subtle temperature fluctuations lies a pattern so unnerving that scientists dubbed it the axis of evil, a mysterious alignment where the CMB's hot and cold spots seem to line up with the cosmic web's largest filaments. It's as if the universe's oldest light and its current scaffolding share a hidden axis, a cosmic spine pointing towards something we can't yet see. This isn't just a curiosity, it's a full-blown crisis for cosmology. The Big Bang Theory predicts the CMB should be isotropic, its variations scattered randomly like paint splattered on a canvas. Instead, when researchers mapped these fluctuations, they found an eerie correlation. The largest temperature variances trace the same rough plane as the superclusters and filaments we see today. The odds of this happening by chance, less than 1 in 100. To skeptics, it's a fluke, a trick of statistics or observational bias. To others, it's a sign that our universe might be stranger and far less random than we ever imagined. One camp argues this alignment is nothing more than a mirage. Our galaxy's motion through space creates a Doppler-like distortion in the CMB known as the kinematic dipole. Subtract that and some claim the axis vanishes. Others counter that even corrected data retains the signal, particularly when cross-referenced with independent filament maps from galaxy surveys. The Planck satellite's painstaking measurements only deepen the debate. Its all-sky maps confirmed anomalies along the disputed axis, but couldn't definitively pin them on systematic error. Then there's the radical interpretation. The alignment is real, and it's telling us the universe has a preferred direction. This idea appends the cosmological principle, the bedrock assumption that the universe looks roughly the same in all directions. If true, it could mean our cosmos is shaped like a vast, rotating torus, or that we're embedded in a gravitational wave so colossal it warps everything around it. Some theorists even float the idea of a pre-Big Bang phase, imprinting this axis a relic of whatever came before our universe's birth, the most tantalizing clue. The filaments aligned with this axis aren't just any structures, they're the universe's most massive superhighways, like the Sloan Great Wall. Their sheer size might magnify primordial asymmetries, turning subtle quantum fluctuations from the Big Bang's first moments into cosmic highways pointing the same way. Upcoming CMB experiments like CMB S4 aim to dissect these anomalies with razor precision, hunting for patterns that could confirm or shatter the axis's reality. For now, this alignment remains one of cosmology's most electrifying loose ends, a whisper that the universe might not be the formless expanse we assumed, but a place with hidden geometry, direction, and perhaps even a shape we've yet to fully perceive. Whether artifact or revelation, it dares us to question whether the cosmic web's threads are woven with deeper purpose, or if we're simply seeing patterns in the void where none truly exist. Rising like ghostly chimneys from the Milky Way's core, the Fermi bubbles stretch 25,000 light-years above and below our galactic plane, twin lobes of superheated gas blazing with gamma rays. Discovered in 2010 by NASA's Fermi telescope, these colossal structures have long puzzled astronomers. What cosmic fury could have carved such immense cavities into our galaxy's halo? But the real twist lies beyond their edges. Recent sky surveys reveal these bubbles aren't solitary anomalies, they're aligned with nearby cosmic filaments. Their gamma-ray glow tracing the same invisible pathways that thread through the intergalactic void. It's as if the bubbles are roots and the filaments are branches of some vast, unseen tree connecting the Milky Way to the cosmic web. The leading theory points to our galaxy's supermassive black hole, Sagittarius A, as the sculptor. Around 6 million years ago, this behemoth might have awakened in a cataclysmic feeding frenzy, its relativistic jets punching through the galactic disk and inflating the bubbles like cosmic balloons. The energy required is almost incomprehensible, equivalent to 100,000 supernovae exploding in unison. Yet there's a snag. The filaments these bubbles touch are hundreds of thousands of light-years away, far beyond the black hole's immediate influence. How could a local event reverberate across such cosmic distances? One possibility is that the filaments acted as conduits, channeling the outburst's energy like lightning rods. Magnetic fields threading these structures could have guided charged particles outward, leaving trails of gamma rays in their wake, but darker explanations lurk in the shadows. Certain filaments intersecting the bubbles show anomalous gamma-ray excesses precisely where models predict dark matter particles might collide and annihilate. If true, the bubbles could be more than remnants of an ancient explosion. They might be windows into dark matter's hidden interactions. Simulations suggest that if dark matter clusters at filament junctions, its collisions could produce the very high-energy photons Fermi detected. The bubble's symmetry, their near-perfect alignment with the galactic center, hints at a deeper link between Sagittarius A and dark matter's invisible scaffolding. Could the black hole's past activity have stirred up nearby dark matter, triggering cascades of annihilation? Or might the filaments themselves be funneling dark matter toward the galaxy, fueling periodic outbursts we've yet to comprehend? The enigma deepens when examining the bubble's edges. Unlike supernova remnants or stellar winds which fade diffusely, the Fermi bubbles have razor-sharp boundaries as if contained by some unseen force. Filament magnetic fields could explain this, their vast lines of force acting like cosmic walls, corralling the bubble's plasma into precise geometries. Alternatively, the bubbles might be propagating through pre-existing weaknesses in the galactic halo, their paths etched by the Cosmic Webs gravitational tapestry. X-ray observations from the E-Rosetta telescope reveal faint, filament-like tendrils extending from the bubble's caps, as if they're straining to reconnect with the larger web. What's at stake isn't just solving a local mystery. If the Fermi bubbles are indeed entwined with filaments, they could reveal how galaxies communicate across the cosmic web, sharing energy, matter, and even information through these invisible highways. Upcoming gamma-ray telescopes like the Cherenkov Telescope Array will scan these intersections for subtle fluctuations, hunting for clues to whether we're witnessing ancient black hole fury, dark matter's echo, or something even stranger. Until then, the bubbles stand as a reminder that even our own galactic backyard is woven into the universe's grandest structures, and that the cosmic web's influence might reach far closer to home than we ever imagined. From missing baryons to ghostly magnetic rivers, from the eerie synchrony of the dark flow to filaments humming with resonant energy, what we've uncovered today isn't just a list of cosmic oddities. It's a testament to how much we don't know. The universe's grand tapestry, woven with filaments of gas and dark matter, is far more than a backdrop for galaxies. It's a dynamic, living structure teeming with anomalies that defy our models, challenge our instruments, and whisper of physics beyond our grasp. Think of it this way: every time we solve one cosmic riddle, the universe hands us two more. The Sloan Great Wall shouldn't exist at its scale. The Lyman Alpha Forest shouldn't clump so chaotically. The Fermi bubble shouldn't align so perfectly with distant filaments, yet here they are, refusing to fit neatly into our equations. These aren't just gaps in knowledge, they're doorways. Doorways that could lead us to finally understanding dark matter's true nature, or the hidden mechanics of space-time, or even clues about what lies beyond our observable universe. And that's the thrill of it all. Science isn't about having all the answers, it's about chasing the next question. Maybe you'll be the one to crack one of these mysteries. Maybe a comment you leave below, your wildest theory about primordial black holes or quantum filaments, will spark the idea that changes everything. The cosmos is waiting for fresh eyes, new perspectives, and relentless curiosity. So stay hungry, watch the skies, follow the missions, the James Webb's next deep field image, Lisa hunt for gravitational waves, the SKA's radio whisperings from the cosmic web. The greatest discoveries in astronomy have always begun with someone staring into the dark and asking, "What if?" Subscribe, join the conversation, and keep wondering. Because the universe, it's just getting started, and the next revelation, the one that rewrites the textbooks, could be just over the horizon. Until then, keep looking up. The cosmos has secrets left to share.